So, we have seen the algorithm A star, and we kind of compared it a little bit with best first search, and we saw that best first search is only concerned with looking at the goal node, and it kind of heads off straight towards the goal. But unlike hill climbing, it does not get stuck at a local optima because it is a global search. A star is concerned with finding the optimal cost path, and it looks both at how close it is to the source and how close it is estimated to be to the goal, which means that it ends up doing more of the search, more of the space it ends up exploring. So, let us look at some variations of A star, which try to trade off between find out trade off between best first and A star. We want algorithms which will terminate faster, because eventually depending on the heuristic function, the space and time requirements of A star tend to be exponential. So, what is happening with A star, that there is a pull towards the source and there is a push towards the goal. Essentially, you can think of G of n as pull towards the source and H of n as pull towards the push towards the goal, essentially, or you can say it is also being pulled towards the goal. What we have done here is we have added a constant here W, and this algorithm which uses W is known as the weighted A star, and it determines how much impact or the relative influence of the heuristic function as opposed to G of n. So, at one end of the spectrum, as you can see, the weight can be 0, in which the pull of the source is the only dominating this thing, and then when weight is equal to 0, when Fn equal to Gn, then if you remember, then that is how branch and bound worked essentially. At the other spectrum is when W tends to infinity, which is another way of saying that G tends to 0, and then it is only the push towards a goal that is dominating this thing. And if you remember, the reason why we chose heuristic functions was for speedy termination of the algorithm. Now, of course, A star has both G of n and H of n. So, let us see if what happens when we vary W essentially. So, this algorithm is called weighted A star, and this figure is only to illustrate the fact that how a combination of G plus H changes the behavior essentially. So, if you look at this graph carefully, we have a start node on the left and we have a goal node on the right, which is on the same line. There are two paths that we have drawn from the start node to the goal node, one going from the top and the other going from the bottom. Both the paths have 5 intermediate nodes, all on a horizontal line. The only difference is that the top path, the 5 nodes are shifted 1 square to the right, and in the bottom part they are 1 square to the left essentially. Now, what we have written in blue are the Manhattan distances to the goal. So, for example, this value is 60 and then 50, 40, 30, and then goal of course is 0. And on the bottom you can see that we start with a Manhattan distance of 70. So, when the weight is 1, we see that illustrative example which I want to use to illustrate weighted A star, and we will look at a couple of variations where W is equal to 1, which is A star, and W is equal to 2, which is weighted A star essentially. So, if you notice in this graph, there is a goal node, start node on the left and a goal node on the right, and there are two paths that we have drawn. Both paths are of equal length. If you look at their lengths, the horizontal segment is 12 units and the diagonal segments are 24 and 36 units respectively, depending on whether it is a longer, bigger triangle or a smaller triangle. But if you sum them up, 36 plus 12 into 4 plus 24, it will be the same cost of 108 essentially. Now, what we have written in these cyan rectangles are the G values of the nodes that we are interested in essentially. So, you can see that for example, 24 plus 12 gives us 36 plus another 12 gives us 48 and so on, and the same G values are kind of repeated on the top essentially. In blue, next to each node we have written the Manhattan distance, and there also you can see that many of the nodes have the same Manhattan distance. So, that is 60 and 60 and so on essentially, except that there is a node which appears to be farther, which is with a value 70 here, which is in the lower path essentially. So, what happens with weighted A star and with best first search? So, best first search only looks at the distance to the goal. So, it will start with this node with this value 60. So, when it generates the two successors, one has a value 60 on the top and one has a value 70 on the bottom. So, best first search will start with 60, generate its successor which is at 50, then 40 and 30, and as you can see it is monotonically decreasing. So, best first search will shoot off on the upper path essentially. When we use weighted A star, we are using the formula G of n plus 2 times h of n essentially. So, if you look at the first node that both of these algorithms inspect, on the top path the h value is 60 and the G value is 36 because the length of that edge is 36. So, the f value used by A star is 96, but the f value used by W A star will be 60 into 2 which is 120 plus 36. So, this one is 60 into 2 which is the h value plus 36 which is the G value. So, this is G and this is h value. On the bottom half, the first nodes that they both see, A star sees a value of 94 which is as you can see 70 plus 24. W A star sees a value of 160 which is 24 plus 2 into 70. So, 164. So, you can see that W A star sees a value of 164 and for the bottom node and 156 for the node on the top, and when it generates the successor of 156 its value becomes 148. Now, you see that because the weight of h of n is higher, the closer you go to the goal the more rapidly the f value decreases. So, from 148 it goes to 140 then to 130. So, both best first and W A star simply take the upper path and do not even look at the bottom path essentially. What about branch and bound and A star? Branch and bound looks only at G values. So, initially of course, it will explore the node which is at a distance of 24 which is the first node on the in the bottom path. Then the next node will have a value of 36 which is the same as the first node in the top path. This has a G value of 36 essentially. So, it will choose between one of them and then after that the G values simply remain the same 48, 48, 60, 60 both on the top path or the bottom path. So, they will explore both the paths visiting nodes alternatively. The same will be true for A star. A star, the red values shown inside the nodes are the f values as seen by A star. It starts with 94 on the bottom left, then it sees two nodes of with f value 96, it will look at them one by one and then it looks at the next nodes which are 98. So, it will look at both the nodes essentially. So, what we are trying to illustrate here and we will see this with another example is that best first and W A star which are more focused towards a goal, they head off towards a goal as soon as they can, whereas branch and bound and A star are both conservative and they keep trying to see if there is a cheaper path that they have missed or not essentially. So, the graph that we had seen earlier, let us see how WA star operates on this, and where W is 2. So, the weight is 2, as you can see f of n is equal to g of n plus 2 of h of n. The values written in blue are 2 into h of n. So, you can see, for example, for this bottom value, it should have been at this 2 hops, which is 20 units away, but 2 into 20 is 40 essentially, and like this for every other node, the h values are doubled essentially. So, the start node is at 200, A star would have thought that it is 100 essentially. The h costs of course do not change. So, let us see how WA star performs on this same graph that we had seen earlier, and let us progress see the progress of how this weighted A star with W equal to 2 performs on this. So, this is what is happening. It is starting with the node with a value 200, and since G value is 0, so the F value is 200. As before, we will generate the nodes one by one, and we will color the nodes in the same manner, where the cyan or green nodes are the nodes on open, the yellow nodes are the nodes on closed, and this red arrow tells you that of the nodes on open, which is the best node. This thing. So, you can see that of all the nodes, this has a value of 181. How did this 181 come from? It came from 160 plus 21, and 160 is twice into the Manhattan distance, because our weight is 2 essentially. The other nodes, as you can see, have values of 222, 262, 269, 257 and so on. So, this is how the algorithm proceeds. It looks at this value of 1673. So, one thing you will notice in WA star is that the F values, as you go towards the goal, decrease more rapidly than for A star. In fact, for A star, F values actually increase, as we will see later. So, that is a third node, and then the fourth node. Now, the way that up to this point, both best first and WA star pick the nodes in the same order. The only thing is, because WA star keeps track of the fact that where is the cheapest path coming from, it has marked this as a parent of this node, which has a value 184, whereas best first had marked this as a parent, and that was the final path it had reported. We will look at these paths again in a moment. So, otherwise WA star heads very rapidly towards the goal. This node that we have, all algorithms explore this node, but there is no path going towards a goal. So, they have to switch their attention to something else, and which is what WA star is also doing. And here is the algorithm, this thing. It is exploring less space than A star. We will look at the A star state space again in a moment, but this is what WA star has done. It finds a path to the goal after inspecting 9 nodes. A star, if you remember, had inspected 14 nodes. Best first had inspected 8 nodes essentially. It found a path of 153, and that was more expensive than the path found by A star, which was 148, but A star had seen more nodes essentially. So, this was a path found by best first. So, as I had pointed out, best first thinks that this is the path, because that is the first path it discovers. It does not reassign parent pointers. It looked at only 8 nodes in the order that we have seen here written inside the nodes. So, this was 1, and this is 2, and then 3 and 4, 5, 6, 7, 8. So, it saw these 8 nodes, and it found the path which was of length 195. Branch and bound, of course, searches the entire tree, and it found the same path as what A star had found, its value of 148 essentially. This is the A star algorithm that we had seen earlier, and you can see that it has found the same path as what branch and bound has found, going from the bottom part of the screen. But it has explored fewer nodes than branch and bound. It has explored only 14 nodes, and it has found the optimal path. And this is one of the things that we had shown that A star is an admissible algorithm. It always finds the optimal path as long as the heuristic function is underestimating. Then these are the 4 variations that we have studied. So, let us just compare them here. We have this weighted A star where W is a weight. If W is equal to 0, that means we are only looking at G of n, then it becomes like branch and bound, and it's generated 23 nodes, inspected all 23 nodes, found a solution with a cost of 148, which is the optimal cost. The same was found by A star also, where A star the weight is 1. So, that is why we have written the weight 1 here. It explored 19 nodes, it generated 19 nodes and inspected 14 of them. That means 14 nodes will be in the closed. It also found an optimal path of cost 148. Weighted A star with a value of 2 generated 17 nodes, inspected 9 of them, and as we just saw, it found the solution with a cost 153. Now, as you can see that weighted A star does not give you the optimal path. What is the reason behind that? Is because when you say 2 into h of n, then you are not underestimating the distance to the goal, at least you are not guaranteed to underestimate the distance to goal. And the condition for admissibility that we had said was that the heuristic function or the heuristic component, which is this whole component W into h, must underestimate the distance. So, in W A star this is greater than h star of n, and which is why, as you can see, in fact it did not find the optimal path. The fastest algorithm was best first search, where you can, as we said, you can think of W as infinity, which is equivalent to saying that G of n is 0, because only h of n has a contribution. It saw only 8 nodes, but it found a much longer path of 193 length. So, these are the 4 algorithms and the search spaces that they have explored. On the top left you see branch and bound. It explored the entire graph of 23 nodes and found a solution with cost 148. Then below that is the next algorithm, which is also admissible, which is A star. It saw 14 nodes and found the same path as branch and bound had done of cost 148. Then on the top right we have W A star with W with a value of 2. We saw that it explored 9 nodes and found a cost of path of a cost 153. And in the bottom, the algorithm we started with, which is best first search, it inspects only 8 nodes and found a path of cost 195 essentially. So, you can see that as W increases, the amount of space that the algorithm explores becomes lesser and lesser, but at some point there is a point where it crosses the bounds of admissibility and it may give you paths which are not optimal essentially. So, in this example W is 2 and it had inspected only 9 nodes as opposed to 14 by A star, but it did not give us an optimal cost path essentially. So, next we will look at some admissible variations of A star essentially. We want to look at variations which require less space, but are admissible at the same time essentially. So, we will do that next.
So, can you explain more on the value of the H function will reduce when we reach the goal node?
Yes, the heuristic value will keep decreasing as you go towards the goal node. As you can see in all these graphs that we have drawn, that is happening, written with blue nodes essentially. So, or maybe we should look at a bigger graph. So, this is A star graph. The source is at an H value of 100. That is because it is sort of 10 hops away from the goal and each hop is 10 units. The farthest node is 140, which is farthest from the goal, but as you come closer towards the goal, you can see that H values keep decreasing essentially. But what is a point I made in the passing, and we will see that shortly, is that the f values increase as you go towards the goal. Why is that? The reason is that this f value is g plus h. While g of course increases as you go away from the source node, h is decreasing essentially as you go towards a goal node. But the contribution of h to f keeps decreasing as you go towards a goal node, and it was the heuristic function which was underestimating the distance to the goal. So, remember that this h of n is less than or equal to h star of n. So, as you go towards the goal, the contribution of the heuristic function becomes lesser and lesser. At the goal it becomes 0 essentially, which means that the f value becomes more and more accurate as you go towards a goal, because the g values are of course completely known, that g values are the best values for that. So, we started with a g value of 100, as you can see with the at the start node. That is because the h value was 100 and g value was 0. Then if you follow the path, the solution path, then that 100 went up to 101. Why was that? Because the heuristic value was 80, but the actual cost was 21 essentially. So, it became 80 plus 21. Then the next node had a f value of 143. So, you can see that it is increasing. We started with 100, we go to 101, 143, then 144, then 145, then 146, and eventually peaking at the goal essentially. The reason why the f values are increasing is because g values are obviously increasing because they are the actual path cost, but h value is the estimated distance to the goal, and it was h value which was kind of underestimating the distance, and therefore it looked closer than it was. And the whole idea of using an underestimating function is that you have a lower bound on the actual path through the goal. So, the actual path through the goal is 148, as you can see, that is the optimal path. But at every other point on the path, and in fact in every other point in the search that space that A star explores, the f values are less than the optimal cost, and this is one of the lemmas that we had proved, that any node it expands will have a f value of less than the optimal cost.
Okay, am I correct that the heuristic value, the importance of heuristic value is much lesser when we reach towards the goal?
Yes, in a way what you are saying is right, because there is a smaller distance left to cover and a larger distance has been covered. So, the g value of course goes into the f value, and it is a decreasing h value which is going, and because its impact is less and less, the f value actually goes up, because it is the heuristic function which is underestimating the distance.
Okay, if I constructed a weight function with respect to the heuristic value, will it be optimal?
So, that is what we are doing with
Currently, we are using a constant weight. If I create a weight as a function of heuristic value,
a variable weight.
yeah.
Well, I am not sure whether people have thought about it, but it is an interesting exercise to 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 see that happens. If you look at this weights on WA star for the same problem, where we have used 2 into h of n, you can see that here the f values are not increasing, here they are actually decreasing essentially. That is because the heuristic function is no longer underestimating the distance. So, if you know that the actual distance for the start node to the goal node is 148, we know that, right, because we have found the optimal path. But weighted A star is thinking it is 200 essentially, but and because the weight of the heuristic function is higher, the closer it goes to the goal, the more rapidly the f value drops essentially. So, as you can see on the path that it has found, it goes from 200 to 192 to 184 then it goes up to 206 again, but then again comes down to 190 and eventually to 153 essentially. This f values increasing is not a phenomenon here essentially. We will see in a little bit of maybe in the next session that under certain conditions the heuristic function behaves in a very interesting way, which kind of makes the behavior of A star closer to Dijestra's algorithm, which means that when it finds a path to the goal, to any node, it has found the optimal path essentially. So, if you look at this W A star, it found this node with the cost 181, then it found this node with cost 173, then it found this node with a path coming through this way essentially, but its value was 226. In the next step, it discovered that it was not 226, but it was 184, which means this node had already gone on to closed with a it had found a path of 226, and later it found a better path to that node essentially, and we will see that when the heuristic function satisfies the condition known as the consistency condition or the monotone condition, it always finds the optimal path to any node on the way essentially, which will have its own implications as we will see essentially.